So last week we were looking at this situation in which we had an airplane that was going to be taking off from the end of a runway, and its initial velocity was 0. And I think we had something like a time, and since I don't have the book in front of me, I'll just make up a new time, but say it's 13.5 seconds, and we know an acceleration, let's say, of 5.4 meter per second squared. We wanted to find the distance traveled, so the displacement from the starting position to the end position. And we realized that we had a problem, and that problem was that we had these basic equations of motion to work with. One of those was the displacement being a function of the velocity and the time, and the acceleration being the rate change in velocity. So we tried to do this with our basic equations, and we wound up getting about twice what we should have had. Well, there's a pretty good reason for that. It really has to do with the fact that we are accelerating. And if you remember, we had our position time graphs, and I think I alluded to this just before we left, and that this graph is actually a curve, right? If we're accelerating, the position as a function of time makes a curved graph. And so it's not like we had constant velocity graphs where our position in time was completely linear, so that it becomes, for that, a simple product of velocity and time. So one way that you might consider doing this is finding a velocity, knowing the acceleration and time, and then putting that back into the equation since you know the time to find the displacement. Well, that gives us twice what we need. Well, there's at least a couple reasons for that. One is the fact, of course, that we are dealing with accelerated motion, and so the graph really is a square function, but more so requires more than one equation to solve that, and the concept of an average velocity. So remember that any true average is just a fraction of the sum of those individual values. So if there's 3 of them, you take 1/3 of that. If there's 2 of them, you're going to take 2. So we'll take an average of those 2 velocities and of the final and initial velocities, and that will give us an average. Now, if we were to solve it that way, yes, it could work. Using the average velocity times the time, we get half of that value we'd otherwise using those 2 equations. Well, this leads us to the idea that maybe we can solve physics problems with a single equation. And if you think about it, we can start manipulating these simple equations with a concept of averages, and we're going to come up with a really dynamic set of equations. We call them the equations of motion. We're going to start from the idea that we have this average velocity, okay? And using this average velocity in conjunction with our simple displacement equation will allow us to derive one of those equations. So delta x being equal to an average velocity times a change in t, and substituting in here, you see that we have 1/2 of the final velocity plus the initial velocity times the change in t. That gives us a function for displacement. That's actually one of those equations. So we don't need to know what the acceleration is, as long as we can find an average velocity and have time. Our second equation requires the use of the generic equation for acceleration. Let me break that out a little bit further. So if the acceleration is the change in v over the change in t, that's the final velocity minus the initial velocity over the change in t. Well, this basic equation can be then solved for a final velocity. or an initial velocity, but I'm just going to solve it for the final velocity. So a final velocity being equal then to, algebraically, an initial velocity plus the acceleration times the change in time, right? We solve for VF. We're going to multiply both sides by delta t, and then we'll add VI to both sides. Okay. One might say that is a equation of motion in and of itself. So we could identify it as such. But the power comes in now in that what would happen if we substituted for final velocity to that first equation we derived? Right there. It's a bit of interesting algebra, but it's not unsolvable, if I can use that word. So that's going to be 1/2 VI plus A delta t plus VI times delta t. Okay. Not too scary. A VI plus a VI is a 2VI, so that's half of 2VI plus A delta t times delta t. And if we distribute and bring the delta t in, half of 2 is 1, so that's VI times delta t plus 1/2 of A delta t times delta t, so it's 1/2 A delta t squared. Turns out that this equation here is very powerful. It's one that Galileo actually discovered in his law of falling bodies, so we'll call that number 2. Well, the third equation really is going to be a combination of this same equation here and our equation here. In the first case, to find the second equation of motion, we substituted in for final velocity here. Now we're going to do it a little bit differently. So our third one will be starting with equation 1, delta x, 1/2 VF plus VI times delta t. And we're going to solve the equation of VF is equal to VI plus A delta t. We're going to solve that for time. So the delta t then would be equal to the final velocity minus the initial velocity over the acceleration. A bit of algebraic manipulation, and then we'll put that back in here. Initially it starts to look messy, but it isn't that big of a problem. Delta x is equal to 1/2 of VF plus VI times VF minus VI all over A. Okay, no worries, no worries. Remember, this starts to look a lot like our function A plus B, A minus B. And that generates a perfect square, doesn't it? So that then is going to be VF squared minus VI squared all over 2 times the acceleration, that being equal to delta x. Now, generally, this equation is expressed as a function of VF, in this case VF squared. So VF squared is going to be equal to VI squared plus 2A delta x. So that's equation 3. So we have these 3 marvelous equations of motion that will allow us to solve a good number of problems. And notice in the first case, we know nothing of the acceleration, but we can relate position to a function of velocity and time. In the second case, we know the initial velocity, but we don't know the final velocity. We can still solve for displacement. The third case, we know nothing about time, and yet we can solve equations for displacement, acceleration, or velocity in the absence of time. Very important is that the equations of motion make a huge assumption, and that assumption is that the acceleration is constant. Just like our graphing exercises, if that acceleration is non-constant, then we can't solve them. So in this case, using these equations moving forward, we have to assume that the equations of motion will operate under the condition of constant acceleration. Okay, let's go back to that problem we had with the aircraft. Okay? So with this problem, we were dealing with accelerated motion. If we assume that the acceleration is constant, then we can use those equations of motion. We wanted to find the displacement. So I always like to do this. I like to rewrite those equations of motion and have them at hand when I'm solving my problems. So I have two expressions for final velocity and I have two expressions for displacement. So I'm just going to write them here. And now let's see, take a look at our knowns and unknowns. So we know the displacement is an unknown, and the final velocity is an unknown. We don't know what that is. So the final velocity and the displacement are unknowns. So that would say that we would need to have two equations to solve that problem. The magic of the equations of motion, as we've seen, are that we can eliminate one of those variables by combining two equations. So if we go through my checklist then, I know that the initial velocity is 0, final velocity is an unknown. My acceleration, I'm just trying to remember, but I think say it's 5.4, whatever. And the time, or the change in time, is 13.5 seconds. The question asks us to find the displacement, so we'll go through our list. Will this one allow us to do it in one step? No, because I don't know the displacement. How about this one? No, because I don't know the final velocity. How about the third one? At first glance, it may not look like it, but what was the initial velocity again? That initial velocity was 0. If the initial velocity is 0, this term disappears. Do we know the acceleration? Yes. Do we know the time? Yes. Therefore, we can solve it using this equation number 3. So I will just rewrite it as VI delta t plus 1/2 A delta t squared, recognizing that that's 0, so the term disappears. You're left with 1/2 of 5.4 meter per second squared times 13.5 seconds. Watch the sign and the exponent, 2 squared. So plugging that into my calculator, I get something like 492 meters. And I'm not sure where that is compared to what we had before, but maybe it's ballpark. Well, what if you tried this way? So using just our simple equations of motion, which we now see are obsolete, we can no longer use them in accelerated motion to find things like displacement. Okay, well, if you tried it that way and you solve for the final velocity, you would say A times delta t, which is 5.4 times 13.5 seconds, and you would get 72.9 meters per second. Okay, and then you might have thought, well, if we just take delta x as velocity times time, that being 72.9 meters per second times 13.5 seconds, you get 984. And notice that that's twice what it should be. Now, the beauty here, again, is that not only can we solve this problem with one equation, but we should be able to go back for each of these equations and find the same displacement. So, prove it to you. We could use the second equation, since I solved for the final velocity here, 72.9. If I used equation number 2, delta x is equal to 1/2 of Vf plus Vi times delta t. Okay, 1/2 of 72.9. Stop. This can be a problem. Because if you're traveling at constant speed, you could actually put 72.9 in here again, right? So then you get half of twice as just what you started with. This time it's 0. I'm just saying you could use this in other situations for constant speed. Times are 13.5 seconds. And you see we're using the average velocity now, aren't we? So half of 72.9, 36.45 times 13.5 is 492 and change meters. It's the same solution, right? Powerful, very powerful. Try another one.